welcome to the lecture of this finite volume method. What are the solution procedure that you can adopt? So, that comes under the solution of the discretized equation. Essentially, this is what I am trying to solve my Ax equals to b, that is my step 4 or the final step. Now, what are the methods? So, one approach could be direct approach. Now, direct approach means what do? That means I have Ax equals to b, I will directly get x equals to A inverse b. So, what does it mean? That means I am directly trying to get the inverse of this A, which is not a easy task, because you think about it, even 2D system, the n by n system, the number of operation that one required to do is order of n cube. So, which is large, and sometimes since this system A is not going to be smooth function, okay, or smooth matrix, this could be a problem of getting the direct inversion. So, that is why it typically A is sparse, large system, okay. Sometimes it could be banded, okay. So, it depends on the kind of PDEs that we are solving for. Now, so what it does, the direct approach is not that well accepted, okay. So, what essentially one uses is, I mean, not very often the direct approach is used, it is very rarely used in CFD solution, okay, because one of the biggest disadvantage of this particular direct approach is that your large computational resources, that is one of the requirement. So, it requires large computational resources, then also high storage. Storage means we talk about in the computer architecture, storage in the sense memory. So, the RAM requirement, high storage requirement, because the linear system. So, this is where the problem comes, that you require very large computational resources, you require high storage requirement. So, that is why very rarely use this CFD in, and top of that, the when the size of A, if A is too large, then it becomes just impractical for large scale problem. So, that means most of our realistic problem are large scale problem, and once you have a large scale problem, that A becomes large and you can get an idea what kind of A, even 2D n by n kind of system, and the number of operation required order of n cube. So, it is quite impractical for the, and also it is time consuming. So, it is really time consuming process. So, what is the alternative? Alternative is that people which often used is the iterative process, okay, iterative approach. So, the iterative approach, I do not get the solution directly, this is not done directly A inverse, rather I will do a iterative process, get solution for x, okay. So, that is done iteratively, and that works on more like an guess and correct kind of procedure, because once you try to solve iteratively, that means you do not have the exact solution and you are not trying to get the inverse directly. So, what you try to do, you initially guess some solution, try to find out the solution, look at the correctness of the solution, you update it, and one of the simple method you can think about is the Gauss-Seidel method. So, what it does, this is one of the simplest of the lot, or it is a very simple method. So, in a Gauss-Seidel method or the Gauss-Seidel method, what it does, the algorithm is very simple. You first you do guess the discrete values of t at all grid elements in domain. Here we are talking about element because we are talking about the cell center value. So, keep that in mind that we are talking about cell center value. This particular approach has nothing to do with the numerical technique that you use, whether it is a finite difference method or finite volume method, because it can be applied to any numerical method. It is essentially applied to a linear system. Once you get a linear system, you can apply it to any method. So, it does not have any restriction what kind of method you adopt. So, essentially it first guess the values. For this particular example, we are talking about the cell center values. So, essentially it is assuming in all elements. If you do have a finite difference, you get all the nodal points, it will assume in all nodal points in the domain. So, then you go around all the elements, or in turn update T by this equation, like Tc equals to minus f AF TF BC by AC. So, you do that. So, essentially the right hand side of the equation, you take everything on the right hand side, then you get this particular system, you update that. So, if you are, let us say you are going from 1, 2 like that to n, when you come to 3 you may use the updated value of previous ones. When you come to let us say 10th, you can use the updated value of the previous ones, so that it will be more quickly it will reach to the solution. So, now you sweep all over the domain. So, that means you cover all the elements that in the domain, all over the domain, that means all the elements you have, you cover all the elements, go over it. So, that essentially completes one iteration. Okay. So, that completes one iteration. Now, you put in convergence criteria, check if the convergence is met or not. Okay. If not, if yes, you stop, if not, go back to step, go back to step B and repeat the process. Okay. So, that means you initially at this step you initially guess the value. So, you start with a guess in all the points in the domain. So, if you look at this particular equation in step B, it is essentially taking your all the things at the right hand side and getting directly calculating Tc. So, once you get that value, you sweep over all the domains or all the elements, and once you sweep over all the elements, that completes the iteration, and then you check the convergence criteria. Okay. If it yes, because this is the criteria that you have provided, that how much error you can have and what kind of error you can get, and all these details we will talk. But first you understand these are the issues that come in picture. That means once I discretize the governing equation, that is where I need the numerical technique. So, I just gave you a quick glimpse of the finite volume approach or the finite volume way, how you can actually discretize to get the linear system. Once you get the linear system, you get the solution. So, this is how you can get a solution. This is one of the approach. Now, here we are using another important term of convergence. What do we mean by convergence? We will talk about that. So, this is one of the criteria. Essentially, you can think at this particular moment that It is a criteria to see whether the solution is perfect or not. If that is not, then you go back to step B and repeat the whole process, and that is why it goes on a iteration and iteration, and this is why this is called iterative process. Okay. Because in one iteration you can hardly expect to get the solution converged. Again I am saying solution converged. Why, how, and what are the criteria, that we will see. Okay. But one of this procedure, the procedure we have described here or discussed here, it is not guaranteed to converge to a solution for any arbitrary combination of AC. So, important point here is that not guaranteed to converge to a solution for any arbitrary combinations of AC and A and B. So, this is a important point. So, any arbitrary combination of A and B and AC, it will not satisfy. The criteria that is needs to be satisfied is called the Scarborough criteria. Okay. So, one needs to check this criteria, and this criteria suggests that minus summation of f, where AF is there, by AC, this ratio, this is the ratio, summation of that divided by AC, that means the first part of the updation process. So, that first component if you see here, this must be satisfying some of the criteria. It must be less than 1 for all grid points, okay, and it less than 1 for at least 1 point. So, that means this is a criteria which is strictly enforced in. So, that means when you talk about this any iterative process, and which we will do later on or the later half of the lectures, that what are the iterative process, what are the iterative methods, and different methods, how they are actually evolved, what are the restriction, and those restrictions come from certain criteria. So, it is not that once you arrive at Ax equals to B, you can get a solution. It is not guaranteed. There are restrictions, there would be restrictions, and as a engineer, as a scientist, you are supposed to do those checking, or as a programmer, you are need to put those criteria in place so that you get a solution which will be converged. Otherwise, solution may not converge, you might get all junk. Okay. See, CFD, that is why sometimes people call is a colorful fluid dynamics, because it can get you all sort of a colorful numbers, but the numbers need to make sense, and as a scientist you are supposed to make sure that those numbers are correct. Now, one important things, any linear matrix A which satisfy this particular criteria, satisfies this criteria, okay, they has diagonal dominance. Okay. If you recall your linear algebra, any linear system, if you have a diagonal dominance, that means the solution is easy to get, and I can get the solution quite easily. Okay. Now, what are the advantage of this particular system? If you put down some of the advantage, because since we are talking over, there must be some advantage over direct process. So, one important advantage is that if you look at it, if you look at this particular process, it just goes on from certain steps, and those steps are nothing but doing certain floating point calculations. I have assumed some value here, I have estimated some value here, I have gone all over the places in the domain, I have checked the criteria, if satisfied I stop, if do not I go back. So, these are all essentially floating point calculation. So, the storage requirement is less compared to direct method. So, when you compare to direct method, the storage requirement is less. Second, why that is less? Because the whole thing are computed on the fly. Okay. Because why I can compute on the fly? Again, if you come to this particular step, you see what is the requirement for TC? It just requires the neighboring elements, because this is a summation over the neighboring elements, okay, and this is what it is, the summation over the neighboring elements. So, that makes it quite effective, computed on the fly, because since enter coefficient in domain is not required. Okay. So, third is that the iterative nature of the process, iterative nature of the process of the method, or rather approach, makes it quite suitable for nonlinear problem. So, this is one of the biggest advantage of iterative method, because once you look at the direct method, if the system is nonlinear, you really have trouble finding the inverse. So, this is one of the biggest advantage that you have in the Now, when you talk about particularly the Gauss-Seidel method or Gauss-Seidel method, it is quite rarely used in CFD, or rather regular practice. Okay. The reason is not that, one of the reason is that rate of convergence is very low with large A. So, when you talk about large A, that means it is a large scale realistic problem. So, this is one of the drawback of Gauss-Seidel method, but as I mentioned earlier, this is one of the simplest of the iterative method. So, we just wanted to see how the iterative method works, okay. But this is not the one which is so attractive and used in the real practice, but it is one of the method someone who is actually getting started with CFD, trying to generate or develop his programming code, he can use it very easily. And these days this kind of all this pseudo algorithm, the pseudo algorithm of these linear solvers are essentially available in the numerical recipes. Okay. So, numerical recipes, if you look at it, this is a book written both in C, C++ and Fortran. So, you can get the pseudo algorithm. So, this is not very difficult for someone who is getting started with CFD and getting a linear system, and he can directly solve this linear system using some sort of a direct or iterative solver. But iterative solver, you can get the pseudo algorithm, then only thing that needs to be done is that convert that thing to the particularly in the program. Okay. So, Now there are other methods like Gauss-Jacobi method, successive over relaxation method. All these different iterative methods are also available, and we would be probably discussing that when we talk about the linear system. Now if you move ahead, there are another thing is that, so the one which we have discussed so far is the essentially the element or control volume kind of method or the discretizations. In the sense, my domain or the physical domain or the computational domain, what you call it, the computational domain is actually discretized using some finite elements or CV, control volumes. So another alternative is that called the phase field approach. What is that? If you look at the same problem, now when we did the finite element kind of system, when we divided in the finite number of elements, we had numbered this element 1, 2, 3 like that to 25. Now this patch 2, patch 3 they are same, patch 1 is the insulated surface. So phase field method is something where you, and if you recall in your finite CV, you store the data in cell center, or rather your solves for cell center. That means I have kept my data in each cell center like this. So this is what I have got the solution using finite element kind of based. Now here in the phase field approach, you store the data on the face or the center of the face. So this marked shown here, this actually shows where I am storing the data. So one approach, I had stored the data in the center, that is called cell centered approach. Okay. So that is cell centered approach. Now this phase field approach, what you have got, you store the data on the center of the faces. That means if you look at this individual element or the interior element, they are stored. So why do we do that? So this is quite often this kind of a face centered or phase field approach, or rather storing the data at the center of the face is used to define phase mass flux, okay, while solving convective and flow problem or fluid flow problem. Okay. So, and also if you recall, when we are doing with the cell center and talking about a interior cell, we had certain fluxes calculated at the, or normal fluxes and all this calculated. So this is quite useful in the phase field approach when you store the data at the middle of the cell faces, you are solving a convective problem or the fluid flow problem. Okay. So this is quite handy. And another approach could be, so this is another alternative, but and when you go along with the system and when you discretize the actually the fluid flow problem. So initially we will do diffusion problem, then we will add convection diffusion, okay, then finally we will go to Navier-Stokes. So once you move along this direction, by the time, so when you solve only the diffusion problem, you will see your cell centered kind of approach could be quite handy. When you come down to convection diffusion, you may start seeing the effectiveness of phase field approach, or rather hybrid kind of formulation. Certain values you start storing at the cell center, certain values you start storing at the cell faces. So, that is called a hybrid. And when you go down to Navier-Stokes, actually when you go down here, this hybrid approach of storing the values would be quite handy, okay? Because some scalar values like temperature, if you talk about any species mass fraction, you talk about any scalar, they are quite handy to store at the cell center, even pressure I would say. But if you store the velocity at the faces, that would be handy to compute the fluxes and all these things. That is what I say, it will be quite handy to define the mass fluxes. Once you store here, the definition of the mass fluxes would be handy to do. That is why when you come down to convection diffusion or to Navier-Stokes, the hybrid approach may be desirable, okay. But we will also discuss, if you do not do this, what are the problems. Every approach or mathematics, since it is a numerical technique, there could be certain problems. So, we will also discuss about that, what are the pros, what are the cons with cell centered approach, what are the advantage of phase field approach, what are the disadvantage of phase field approach, what is the biggest gain that one can achieve with the hybrid combination, okay. Now, last one which could be another is the vertex field approach. So, now if you see that vertex field approach, you are now keeping the data at the points. So, that means this is typically that is what we do in the finite difference method, that we store, if I think about a straight line and I am getting a solution from here T1 to T2 in a one direction, it is just one direction, finite difference just store data in every points, okay, compared to finite volume where store the data in the centers. So, this can be converted into finite volume, this will store the data in the centers. So, this is where the difference is. Now, vertex field approach is nothing but storing data at the points. So, these are my internal element, okay, an internal element connected with all other element with certain vertex or certain corners, and those corners are now I will store the data, and when it is handy to keep the data there. So, these are could be some interior vertices which could be common to some elements, which could be the exterior vertices which will actually belong, like these external or exterior vertices, they belong to the boundary condition. So, the importance or the this is more useful for post processing the solution data, post processing, okay. That means when I solve the linear system I will get a solution. When I get the solution, now post processing of the data would be handy when you use this kind of, and so that means when I have a cell centered data, I got the solution here, now I am actually moving the solution to these cell vertices, and if I wrote the vertices, that is more handy for post processing, or in some cases for gradient calculation, okay. So, this kind of a data storage would be handy. Sometimes it would be handy for gradient calculations, or most of the time it is for post processing. So, this is how you get a solution of the linear system, and we will stop here today, and thank you very much.